Okay, so when we're talking about Halley's theorem earlier, we mentioned this idea about relaxing the convexity assumptions so long as the intersections between the sets were contractible. Okay, so let me try to better explain. It's like what one means precisely. It's like by the notion of contractibility. Okay, so this leads to the idea of what is known as homotopy type. Uh, And if you will, it is an attempt to relate spaces, but which is somehow, um, it's like weaker, if you will, than the equivalence between topological spaces, which we're familiar with, which was this idea of spaces being homeomorphic, which is to say that you have, um, it's like maps between two spaces which are continuous, it's like, and which have a continuous inverse. Okay, so we're going to relax that, and we're going to instead, it's like talk about homotopy equivalence instead of sort of topological equivalence. So we introduce a notion of equivalence between topological spaces. Um, that is weaker than topological equivalence. Okay, and of course the usual notion of topological equivalence is that these spaces are homeomorphic. Okay. All right. So let's consider two continuous maps. Okay. So consider two continuous maps. Let's say f and g from between obviously two topological spaces x and y. So a homotopy, okay, between these two maps, right? You should think of as a way to interpolate. Well, not quite interpolate. It's like interpolation comes a little bit later. It's a way to sort of get from one to the other, right? Well, it is sort of a notion of interpolation. Okay, so homotopy between f and g is a continuous map. Let's call it h from x across the interval to y. Okay, such that when you have h and you evaluate a point x and the parameter is 0, right, you just get f at x. And then if you take h and you evaluate at x, but with parameter 1, you get g at x. Okay, so there's a sense again in which you're interpolating. It's like the map f to g. Okay, and of course this turns out to be what is called an equivalence class. So this sort of defines an equivalence class. Okay, and then so we denote this by saying that f is equivalent to g. Okay, in this homotopic sense, right? And f is homotopic to g. Okay. Okay, of course, if there exists a homotopy between f and g. Okay. All right. So let me just stop here for a minute. Okay, so now that we have this notion of homotopy between two continuous maps, we can then use them to this idea to relate spaces instead. Okay, so let's see how you go about doing that. Okay, so this can be used to relate spaces. Okay, and let's look at a particularly simple example, which is this idea of a retraction, before we go to sort of the more general setting. Okay, so the retraction idea applies. It's like when the two spaces are, one space is a subset of the other. Okay, so we say that, let's say y, which is contained in x, right, is a retract of x. Okay, if there is a continuous map let's say R from X to Y, okay, such that R, when restricted to Y, is just the identity map on Y, okay, and then we call that map a retraction. R is sort of referred to as a retraction. Okay. All right. And then a deformation retraction, if you will, it's like it's a way to sort of smoothly go from the identity on X to this retract here. Okay, so we say that Y is a deformation retract. Okay, if there is a homotopy between the map R, right, and the identity map on X. Okay, and if that's true, right, if R is homotopic to the identity its icon X, right, then we say that X deformation retracts onto Y. Okay, all right. And then it's easy to convince yourself that any deformation retract is a retract, but the converse is not true. Okay, so every deformation is a retract, right? But the converse is not true. And if you need an example of something which is a retract but not a deformation retract, you could imagine that, say you have a bunch of unit intervals, it's like, but they're sort of disjoint from each other. So this is 0, 1 cross, so maybe the set 0, 1, 2, 3, right? Okay, and this is what I call X, okay? And then Y could just be the interval 0, 1 cross the 0, right? And R can map, so if this is X, the point X and Y, R can map X comma Y, right, to the point X comma 0. So, so this kind of foliated space, right? Deformation or retracts, it's like to just the one copy, but it's not a deformation retract because you can't smoothly do this, okay, while staying in X. So that's an example of something which is a retract. Y is a retract of this, but it's not a deformation retract of it. So that's sort of an example. Okay. All right. So we you know, recap. It's like we talked about this idea of homotopy. It's like between maps. We used it in this case of relating spaces, one of which is a subset of the other. And then we want to sort of talk more generally about sets which may not necessarily be subsets of each other. Okay? All right. Okay. So let's see how you go about doing this. Okay. Okay. So, so more generally, right? You have two topological spaces. Let's say X and Y are homotopy equivalent. Okay, if the following is true. If now there are two continuous maps, it's like one of which maps X to Y and the other one maps Y to X. Okay, all right, so if there are continuous maps, let's say F maps X to Y and then G maps Y to X. And then, of course, normally it's like in the usual setting, it's like when we talk about topological equivalence, F and G are inverses of each other, right? So if you have a map F mapping from X to Y and a map G mapping Y to X, it's like, and they're inverses of each other and they're both continuous, right? Then, of course, it's like X and Y would be topologically equivalent or homeomorphic, okay? So where's the relaxation, right? The relaxation is that now F and G's are not necessarily inverses of each other, but they're somehow related in some way to things you want inverses to have. Okay, and what would that be, right? So you can look at two possible compositions. It's like of F and G. Okay, so and they're as follows. Okay, so if you take G composed with F, right? So G composed of F is a map from Y to X and then X to Y. So it's a map from Y to itself. Okay, and normally, of course, it's like if it's like G was the inverse of F, it's like this would be, the identity map on Y, okay? So let me just, okay, sorry. So if you have G composed of F, it's like you start from F, so X to Y, Y to X, right? So this would be normally be the identity map on X, okay, if F and G were inverses of each other. Okay, so now instead of having it be the identity on X, you just require that it's sort of homotopic to the identity on X. Okay, so instead of it being the identity, it's homotopy equivalent. It's like to the identity. Okay, and then a similar thing happens if you do the other composition, which is F composed of G, right? So G goes first, Y maps to X, X maps to Y, so it's F composed of G is a map from Y to itself, all right? And then again, normally if they were inverses of each other, this would be the identity on Y, but now I'm just requiring that they are homotopic to the identity on Y instead. Okay, so that's where the relaxation is. Normally these would actually be equal to the relative respective identities, but now we're just saying that they're homotopy equivalent. Okay. All right, so this is sort of this idea of homotopy, and you can ask, well, how is it related? It's like to the idea of retractions, in particular deformation retractions we talked about before. All right, so this reduces to the case of a deformation retract. where F here would be our retraction R, right? And then G is the inclusion map, which maps Y and includes it into X. Right, so this is what's called the inclusion. Okay, and then you can check that, you know, under those identifications, the conditions for homotopy equivalence, it's like lead you to the conditions for deformation retractions. Okay. All right. So now we're ready to talk about, at least formally define for you, then what you know, contractible really means, right? So as you might expect, it's like what is going to happen is that contractible is going to be that you know, basically the space you're working with is homotopy equivalent to a point. Okay. So if Y is a single. All right. So my audio ran out, so I apologize. Um, Okay, so we're talking about this idea of things which are homotopic to a point. It's like, which is the notion of contractibility. So if Y is a single point, right, then we say that X has the homotopy type of a point. Alternatively, we can say that it is contractible. Okay, all right. So anyway, so this is the notion of contractibility, which is relevant when you try to relax the assumptions. It's like of Helly's theorem away from just sets of convex sets. And again, Helly's theorem still holds true if the sets are closed and they have the property that the pairwise intersections are contractible. Okay, so let me just stop here for now.